Hello everyone. In this section, we are going to study the special functions. We study the two functions, Bessel functions and the Legendre functions. The following two differential equations are often encountered in many areas of science. Bessel's function is a solution of the Bessel's equation of order nu, x squared y2 prime plus xy prime plus x squared minus nu squared times y equals 0. So you can easily recognize x equals 0 is a singular point, because if we change this equation into the standard form, we can easily find x equals 0 is a singular point. Also, you can apply the method we learned in the last lectures. X equals 0 is a regular singular point. Then we can apply the method of Frobenius to find solutions. Another equation is Legendre's equation of order n. 1 over x squared times y2 prime minus 2xy prime plus n times n plus 1 y equals 0. So we'd like to find the solutions using the power series. X equals 0 is an ordinary point. First of all, I'd like to show you to find the solution of the Bessel's equations. As I said, we can use a method of Frobenius to find the solutions around x equals 0, because x equals 0 is a regular singular point. So we use exponent of r. So x to the r, we have to multiply. First of all, we'd like to find out the exponent of r. Then substitute this expression into the differential equations. I squared y2 prime plus xy prime has the same power index of the x, so we could combine two terms into the single terms here. It becomes I plus r squares times c sub I times x to the I plus r. Then these last two terms is expressed, power index becomes increased by 2's. So in this case is the mu squares. Then we just only pick up the I equals 0. Then you could find that the first term is expressed r square minus nu square times c sub 0. And the other terms, first term, third terms to combine to the second terms. The second terms is going to become the third terms. Then from this equation, you can create the initial equations to look at the coefficient of the c sub 0. This equation have to be satisfied any value of the x. Then r square minus mu square have to be 0. So from this equation, we could find the exponent of r is plus minus nu. So when the r equals nu, we can express the Bessel's equations. It becomes 1 plus 2 nu times c sub 1 times x plus sigma I start from the 2 to the infinities, I times I plus 2 nu times c sub I times x to the I plus sigma I start from the 0 to the infinity, c sub I x to the I plus 2. Then we can change the I to the j. Using the second terms, we can use the j equal I minus 2. For the third terms, you can use the j equal I. So just we can exchange the I to the j for the third terms. Second terms and the third terms is combined into the single terms. This is the expression. So by looking at this equation, all the coefficient of the x have to be 0. From these terms, this have to be the 0, so you can find this first equation. From the second terms, coefficient have to be 0. We have a second equation. So from the first equation, you can find the c sub 1 is 0. So by using the second equations, if C sub 1 is 0, C sub 3 becomes 0. So C sub 1, C sub 3, C sub 5, all the C sub odd number becomes 0. From the equation for the C sub I plus 2, C sub I plus 2 equal minus C sub I over I plus 2. I plus 2 plus 2 news. So we have already known all the odd numbers is 0. So we just only consider the even numbers for the subscript. I plus 2 is 2j. We substitute, then C sub 2j equal minus C sub 2j minus 2 over 2j times 2j plus 2 new. Then it becomes minus C sub 2j minus 2 over 2 squares times j plus new. So we have these expressions using these calculations. Then we'd like to express the C sub j in general. We have to define the C sub 0. So we choose the C sub 0, 1 over 2 to nu times gamma functions. Gamma 1 plus nu. Gamma 1 plus nu is a gamma function and satisfies these relations. Gamma 1 plus nu equal nu times gamma nu. We use this expression. I have already shown C sub 2i is equal to the minus C sub 2i minus 2 over 2 square I times I plus nu. So we use this relation to express these terms. So it becomes minus 1 over 2 squares I plus nu. So this term becomes minus C sub 2 I minus 2 over 2 squares I minus 1 I minus 1 plus nu. Then we apply the same relations into the here. The equations becomes minus 1 over 2 squares I plus nu minus 1 over 2 squares I minus 1 I minus 1 plus nu times minus C sub 2 I minus 3 over 2 squares I minus 2 I minus 2 plus nu. So you can keep calculating this ways. It becomes minus 1 to the I C sub 0 over 2 to I factorial of I plus nu minus 1 I plus nu minus 2 blah 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 times 1 plus nu. Then you can substitute C sub 0 into that equations. C sub 0 is a 1 over 2 nu. So this is 1 over 2 nu times gamma to the 1 plus nu. And we use a relation for the gamma 1 plus nu equal nu times gamma nu. Then finally we can express this becomes minus 1 to the I over 2 to 2I plus nu factorial of I gamma I plus nu plus 1. Then we derived these relations. So Bessel function, the solution of the Bessel's equations of the first kind is defined by substituting this C sub I into the power series solutions. So J sub nu is a Bessel function is given by these relations. By substituting this C sub 2i into the here. Then when the R equal minus nu we could use the same technique to find the expression of the j sub 1 minus nu. Is expressed this one. The general solution of the Bessel's equation is given by the sum of the two functions of the j sub nu and the j sub minus nu, multiplying the c sub 1 and c sub 2 respectively. So this is a general solution. But this is really important to note. This equation we can use when the nu is not integers. If the nu is integers, j sub nu and j sub minus nu are not independent. So we have to find another form of the solutions. So in the next lectures, I'd like to show you another functions. The graph of the Bessel function is given by. And so you can find that when the case of the nu equals 0, nu equals 1, and nu equals 2, nu equals 3, and nu equals 4. So you can find that the Bessel function is oscillationary functions. Okay, this is the end of this lectures.